Thanks. All right, thanks everyone. By background, I'm mainly a cosmic microwave background cosmologist, but for the last few years I've been pretending to be a radio astronomer, since I think this project, Chime, is especially exciting, and I'm going to tell you about why I think so. So I should start by acknowledging my collaborators. Chime Collaboration has 150 so people in it. That includes everyone from people that design algorithms and write software like me to people that design amplifiers and tighten bolts on things. And most Chime collaborators are mainly at these four institutions, including University of Toronto. There are a ton of people here that work on Chime who are even in the audience. And smaller teams at these other institutions, including Perimeter Institute, where I'm based. So I want to talk, I think the Chime Fast Radio Burst science results are incredibly exciting, and I want to talk about those. But I also want to talk about the larger context of why we built Chime the way we did and what the implications for radio astronomy in the near future. So I want to start with just a general introduction of the Chime concept as I see it. So first, just some high-level bullet points. Chime is a new telescope in British Columbia at JRAO. It's the first new Canadian research telescope in several decades. And it's a compact interferometer that sits on the ground with no moving parts, except for the Earth, which is a moving part. As the Earth rotates, the scanning beam slowly sweeps out the sky. This instrument is 80 meters on a side. The photo maybe doesn't do justice to how huge it is. And hanging off of these feed lines, there are 256 antennas on each of the four cylinders for a total of 1,024 antennas. It observes in the radio frequency range 400 to 800 megahertz, which was selected for 21 centimeter cosmology in this redshift range, where the redshift is too large to observe a lot of galaxies, but too low to observe the Lyman alpha forest. And it's we're very fortunate that this frequency range is interesting for non-cosmological purposes as well. So I'd like to contrast the Chime design with a traditional radio telescope, which is a big dish with one feed or maybe a few feeds sitting at focus. The traditional radio telescope focuses by physical delays in the optics. If a bundle of rays comes in from infinity, then the optics of the telescope have been arranged so that all of these path lengths are the same, and so the rays interfere constructively at the feed, and the source of the rays is in focus. For a bundle of rays coming in at infinity from a different direction, the constructive interference condition would not be satisfied, and the source would be out of focus. Now I want to imagine getting rid of the dish and simulating it in software. And what I mean by that is that I replace the dish, the big piece of metal, by a sequence of antennas, maybe one antenna per wavelength. And at each of those locations, I digitize the electric field. So each of these boxes is intended to represent a 1D array on the computer, storing time samples of the electric field. And then I just combine those samples with some set of time delays, which has been chosen to mimic the focusing effect of the optics. So by digitizing these signals and summing them with the appropriate delays, you can simulate the dish in software and focus on a particular part of the sky. And if you wanted to repoint the telescope to focus in another direction, you would just choose a different set of relative delays. Now you may wonder what this gains, and it gains something very exciting, which is that you can repeat this computation n times in parallel to simulate n telescopes pointed in slightly different directions. Digital time streams may be copied freely. This doesn't destroy information, and you can focus in as many directions as you want, unlike an optical instrument where you could maybe fit one feed or a few feeds, perhaps order 10 feeds at the focus, but fitting more would start to become difficult. And Chime represents an extreme case of this concept, where we have 1,000, and we're forming and processing all 1,024 independent beams in real time. And so this statement sounds too good to be true. For most purposes, it is the case that the raw sensitivity of this instrument is the same 1,024 single-feed radio telescopes with the same collecting area as Chime. That's a big research telescope like Parkes or GBT, all varying in different directions. I want to say a little bit more about how Chime observes. It'll be useful to keep this picture in mind throughout the talk. So a single antenna in any one of the cylinders would observe this so-called primary beam. The Chime design is actually a compromise between optical and software focusing, where the beam of a single antenna in a single cylinder is focused in one direction and unfocused in the other. It goes from horizon to horizon, since the cylinder is focused one way but not the other. And then by beamforming, as previously described, i.e. collecting radiation, digitizing radiation from each of these antennas and combining with different delays, we can form a 256 by 4 array of formed beams with an angular resolution of around 1/3 of a degree. And this whole pattern of primary beam and formed beams is fixed in the coordinate system of the telescope, but slowly rotates on the sky through Earth rotation. So every 24 hours, we get to observe the whole sky with an angular resolution of around 1/3 of a degree. That's the size of the formed beams in the Chime frequency range. Now, when I was thinking about this project a few years ago, I was thinking about it like this. From everything that I've said so far, you might surmise, and for many purposes this is true, that the statistical power of a radio telescope is quantified by its mapping speed, which is the number of beams that you can process or afford to compute. So that's 1,000 for us. Times the collecting area, which is setting instantaneous sensitivity per beam. Times some order 1 factors that I've omitted in this back of the envelope comparison, things like system temperatures, bandwidths, et cetera. So with this crude definition of the mapping speed and in some weird units which are not what anyone actually uses, Chime is comparable to FAST and an order of magnitude or so better than these other famous telescopes. But let's just think about what a ridiculous statement that is. Here are FAST and Chime compared to scale. Could it really be true? A few years ago, I was wondering that FAST, a 500-meter telescope in China and one of the biggest, most ambitious projects in astronomy, is comparable in statistical power to our grassroots effort in Canada with a few percent of the budget. We're all very busy, but we don't think of it as a grassroots effort, but by comparison it is. This just feels like it can't be right. But then this calculation seems too simple to be wrong, so what's going on? So I wasn't smart enough to figure it out, and so if I had realized why this was hard, I might have chickened out. I'm glad that I didn't. And so I'll come back to why this is so hard, but first I want to explain the wonderful things that we would like to do with this high mapping speed. So Chime is, thanks to its high mapping speed, is an amazing instrument for finding fast radio bursts. I'll introduce fast radio bursts properly later in the talk, but for now I want to say that Chime has found, and it is really nice to give a talk with past tense in the slides. For a few years, I was just giving talks that were all forecasts and like trying to get people excited about the new algorithms we were developing. And it's nice to have a talk. It's really nice to have a talk that's mostly results. Fast radio bursts are a high-profile unsolved problem in astrophysics and a very exciting topic. Chime has found around 700 fast radio bursts, whereas to put that number in comparison, the total number found by all other telescopes combined so far is 79. And this has been really become one of the most exciting experiments in the world for fast radio bursts and a flagship project for Canadian astrophysics. Most of our papers have been published in Nature, which is prestigious and sometimes even correlated with being a good paper. The Chime design is very interesting for pulsar timing. Pulsar timing is interesting for astrophysical purposes and also an interesting way to search for gravity waves. If you time all of the pulsars in the galaxy, then when a gravity wave goes through this picture, it will systematically advance pulses along some lines of sight and delay pulses along others. And so you can use all the pulsars in the galaxy as a big interferometer, the same way LIGO detects gravity waves by comparing light travel times between two arms of an interferometer. We can compare light travel times between different pulsars in the galaxy. But the wavelengths are very different. Pulsar timing would be sensitive to gravity waves with wavelengths on the order of a few light years, which would be like supermassive black holes in galaxies, probably at cosmological distances far from merger. Anyway, Chime on its own is not super well optimized for pulsar timing because we're at frequencies that are a little too low. The pulse broadening effects, propagation effects of the interstellar medium go as a large negative power of radio frequency, so that the pulses are fairly spread out and have large timing uncertainty at the low chime frequencies. You would really want to be at frequencies of a few gigahertz to be optimal for timing pulsars. However, there are already pulsar timing campaigns at those frequencies, projects like Nanograv, and some order 1 fraction of their timing uncertainty or noise is due to uncertainty in ISM-related nuisance parameters that we get to measure very well since the ISM is so important for us. So we estimate that Chime's pulsar timing measurements, when contributed to Nanograv, can reduce timing noise by some order 1 amount. So that will make Chime interesting for pulsar timing, but if you were optimizing for it, you would want to do something like Chime, but at higher frequency. A blind pulsar search is also super interesting. Chime has enough sensitivity to find thousands of new pulsars, which would increase the known population by an order 1 factor. I should say that there's a massive computing or algorithmic challenge here, and the number that we will actually find will depend largely on how successful our attempts to invent new algorithms are. And finally, cosmology. Chime's forecasted measurements of the expansion history of the universe are competitive with next-generation large-scale structure surveys like Euclid or LSST. So Chime is relatively inexpensive. The cost is $15 million, which is small for a new project nowadays. And any one of these items would more than justify a larger project. So this may all seem a little too good to be true. So here's why it's really hard. So in this table that I showed earlier, the right column, the mapping speed, or the collecting area times the number of beams, is really the statistical power in principle under the assumption of infinite computational power. But the computational cost is proportional to the number of beams at least, since that's just setting the total data volume. Or maybe worse, maybe the square of the number of beams, depending on what you're doing. So if you're just multiplying A by N, then Chime looks really optimal because it's much cheaper to increase N than to increase A. If you want to build a bigger radio telescope, if you want to build a dish, you have to buy a bunch of metal and reinforce it and have a big counterweight and motors that have to be very sensitively calibrated, et cetera. Whereas it's very cheap to just keep adding antennas to a parameter. However, Chime achieves its high mapping speed by generating this tremendous data volume with low statistical power, like per byte. And so the Chime design is not really a way of getting something for nothing. It's a strategy for moving difficulty from hardware to software. We're saying that we're going to build this inexpensive instrument with very high sensitivity in principle and confront hard problems in software later to process all of the data. And in fact, radio astronomy has, by reputation, is one of the most computationally difficult areas of astronomy. So it was not a priori clear a few years ago that this was a step in the right direction or was going to work. So computing challenges are really central to Chime, so I want to talk about the computing a little bit. When electrical measurements of the atoms, they come in coax cables that go into some custom FPGA boards that convert analog to digital, and also do a little bit of upfront processing, like they FFT the data and split it up into frequency channels. There's some non-trivial network rerouting, which is very convenient to do on FPGA. And just to give a sense of the computational volume, the data rate at this point in the system is 800 gigabytes per day. And when I talk to astronomers, I like to convert this to astronomers' units and say that it's 5,000 copies of the LSST telescope. So LSST is considered like a notorious example of big data in cosmology at 15 terabytes per day. So you can see what we're up against. From there, the data goes into the GPU farm, the correlator, which is the largest part of the Chime system in flops. And what the correlator is computing is the so-called visibility matrix, if you're used to radio astronomy lingo. And if not, what it means is that it's just computing the two-point correlation function between every pair of antennas in the system at a very high time sampling rate, every few microseconds. And that is far too much data, that matrix at that sampling rate, to do anything with, to send it out over the network or write to disk or even write it back to memory. There's not enough memory bandwidth. But any data product that you're interested in can be formed from that visibility matrix. And so these different backends are each constructed to serve a different science purpose, and are asking the correlator to compute some derived data product which will fit over the network. So for example, this one to explain, so every in this is a big computing cluster on site that each other for different products. The simplest one to explain is the pulsar timing backend, which is asking the correlator for each of 10 locations, selectable, the correlator maximum possible information, that is at the maximum frequency channelization and time. But information from the rest of the sky is discovered, is not requested. The Frb Search backend is asks for something different. It asks for locations, all 1,000 beams, but less information per sky location. It just requests total intensity, averaging over polarizations, and intensity at a lower time with 1 millisecond sampling, averaging a bunch of time samples. So collectively, this is sort of a big heterogeneous data center that is all constructed from scratch, and the software is constructed from scratch too, which is really hard. So the search, I like computational problems, and I got interested in the Frb Search Problem a few years ago, and my team at Perimeter, this group of superheroes, wrote the low-level Frb search that processes the data requested from the correlator by the Frb backend into a list of candidate Frb events. And our search algorithm, which took us a few years to devise and implement, is orders of magnitude faster than other search software. I still haven't seen an example of another telescope that we couldn't do on like one CPU. Is near statistically optimal. I think we understand how to weight things a little bit better, and some of the details of the Frb search. Runs in real time with about a 10-second latency, which is very important for a triggered search. We have to do the whole search when there's too much data to write all of it to disk. So we have to do the search when the data is still in a memory ring buffer, and we only write it to disk if the trigger activates and we detect a candidate. And we search a huge parameter space out to a maximum dispersion measure. I'll say what that is later, a high maximum dispersion measure. Even with all of these improvements, we need a dedicated 128-node computing cluster to run the Frb search. This is mainly what we did for the last couple of years, and I used to talk about it a lot, but I think going too far down the computer science rabbit hole is not appropriate for a physics colloquium. So I just want to show like a couple of things for shock value. So here's some ordinary C++ code to take the transpose of an n by n matrix. And you might think that there's no scope for optimizing this. The only thing you could really think of is to see which ordering of the for loops is faster, but I already did that. Here is a version that's 4 times faster. This code also takes the transpose of an n by n matrix. And here's what's going on. Surprisingly, in 2019, it is possible for the human compiler to beat the real compiler, in this case by a factor of 4. If you get really clever about how to use the so-called SIMD registers on modern x86 machines that hold multiple, like 8 floating point values, say, in one register. So this code is reading out the matrix in 8 by 8 blocks in SIMD registers, and then using some combination of assembly language instructions, shuffle the data around and do the 8 by 8 mini transpose and then write the result back. That turns out to be a lot faster. So all of our key, in order to fit the search, and I would basically recommend that all of you just simplify your lives by just pretending that you never saw this slide and never doing this. But it almost never, very human time intensive, and it almost never makes sense to do this instead of just letting the computer run 4 times longer. But we're in the situation where we've built this computing cluster from scratch to just run one code for 5 years, and we've maxed out our hardware budget. There's no room to make it 4 times bigger, and so we actually had to optimize things at this level. I think just this slide doesn't really do justice to all of the computing challenges that we confronted, both low-level challenges like this and high-level mathy challenges. Like at the heart of the Frb search is something called the dispersion transform, which is an integral transform that we figured out how to factor as a sequence of smaller integral transforms, some nice math tricks. The most challenging part of the search, for sure, what we spent most of the time on, is figuring out how to reject all of the human-made radio transmissions that are much brighter than astrophysical signals. Humans make a ton of radio waves through cell phones and other things. Every time an airplane flies over the telescope, it reflects in human-made radio transmissions from a large radius. The RFI environment of Chime is a very complex, time-dependent environment, and figuring out how to get all the different sources of RFI out of the data and do so at this level of code optimization. Like we have a really nice library for doing that where you can compose the RFI strategy from a high-level language like Python, and it all gets compiled into low-level code like this. That was like 10 out of 10 in technical difficulty. It was super hard. And if anyone wants to talk about it afterwards, I'm like really happy to nerd out and tell you all about it. Okay, but I'm very happy to say that after detecting FRBs for about 1.5 years or so, we have a lot of really exciting science results. So I want to talk about the high-level science for 20 minutes or so, and then come back and talk a little bit more about the implications of the Chime design for the future. So I haven't really introduced fast radio bursts yet, so let me say what they are. So very occasionally, a very bright, short, like 1 millisecond pulse of radio emission is observed. Here's an FRB. And the arrival time of the pulse depends on the observing frequency. The delay of the pulse relative to infinite frequency is proportional to frequency to the -2. And that is the dispersion relation expected for propagation through a cold, unmagnetized plasma, which is not too dense. And so the coefficient of the nu to the -2, the total dispersion delay, is what's called the dispersion measure. And you can think of it as counting electrons in the line of sight of the FRB, the line of sight integral of the electron density. And by definition, FRBs are pulses whose observed dispersion measure is larger than can be accounted for by integrating a model of the electron density all the way out to the edge of the Milky Way, suggesting the FRBs are outside the galaxy at cosmological distances. Now, I should say that when FRBs were first discovered, an alternate hypothesis was that FRBs are in the galaxy, and whatever physics just creates a local environment with a lot of electrons. You just get to, when you measure an FRB, you measure this integral, but you don't know whether all the electrons are just piled up at the FRB or close to you or where they are along the line of sight. But over time, the hypothesis that FRBs are very far outside the galaxy at cosmological distances proved to be correct. The observed sky distribution is isotropic. After we saw 10 or 20 or so, that was pretty clear, which means that if they were in the galaxy, they would be preferentially in the galactic plane, of course. This on its own, this observation on its own leaves open the possibility that the FRBs are just in very nearby galaxies. But recently, host galaxies have been determined for a few FRBs, including a Chime FRB that I'll talk about and have a slide on later. When you determine a host galaxy, you can follow the galaxy up in optical or other wavelengths and get a redshift. And so far, all of the host galaxy redshifts have been cosmological. Like a typical FRB would be at redshift 0.2 or 0.4 or so. And that makes FRBs incredibly interesting objects to have their observed brightness from a cosmological distance. They have to be ultra-energetic, something like 1 million times brighter than the brightest pulses we see from galactic pulsars, and frequently occurring. The rate on the whole sky is probably something on the order of 1,000 per day. And so there's something big missing in our understanding of astrophysics that we don't have a good explanation for these ultra-bright, luminous, fairly frequently occurring pulses. And explaining FRBs has really become a central unsolved problem, I would say, in astrophysics. One more thing. So prior to Chime, One FRB out of around 30 that were known prior to Chime had been observed to repeat. And the repeating FRB was a goldmine of information. In particular, it was observed with VLBI telescopes that have very high angular resolution, sufficient angular resolution to identify a host galaxy whose redshift was found to be 0.2. So here's my theory slide. In this talk, I mostly want to talk about observational results, and I cannot do justice to the huge variety of theories that have been proposed to explain fast radio bursts, except to say that people have actually started writing papers that catalog the different theories. And there's like a community wiki you can go to now if you're a theorist to like list your theory and explain what the observable consequences are and how it might be ruled out. I'll talk a little bit about our timeline. So we detected our first FRB in August 2018 and put out, and this is when we were first constructing the system. Like we had just installed a few nodes out of 128. And we put out something called an Astronomers telegram, which I had never heard of before, but there's a website where you can post plots and call them telegrams. In January of 2019, we wrote a couple of papers based on our first month of commissioning data. And this was at a period of time when we were not expecting to be detecting FRBs. We were like still installing computers, debugging software, et cetera. But we nevertheless, in the first month, found 13, including a second repeater, R2, which we thought was really exciting. By June of 2019, we detected the original repeater, which is sort of unsurprising. What actually may be surprising is that the original repeater is not so active at chime frequencies, even though it's thousands of pulses have been detected at frequencies a little higher than chime, like 1.5 gigahertz or so. Last fall, we put out a paper with 8 more repeaters, bringing the total known up to 10. Last month, we published some really exciting results. One of our repeating FRBs, the second one we found, or the third one found cumulative so far, we localized to a host galaxy. I'll talk more about how we did that. We put out another paper with 9 more repeaters. And then very recently, a couple weeks ago, we found something really new, periodic activity in a repeating FRB, which is something that had never been observed before. It's a new phenomenon, and I really think this is one of the most interesting FRB papers in the last couple of years. I should say that this slide does not even really do justice to the amount of data that we have and the number of papers that are imminent. We found, something like 700 FRBs so far, but we haven't published any sort of catalog yet, since in order to do statistics with that sample, so having 700 FRBs is a wonderful opportunity to do statistics, but it also means that in order to do statistics properly, you have to understand like the selection of your instrument. What's the probability that you would have seen an FRB if it had gone off at a particular sky location with a particular set of parameters, dispersion measure, pulse width, and so on. So characterizing the instrument well enough to do population studies is taking time. That's why our papers focus on repeaters. If you see a repeater, then it's just interesting to publish that observation on its own. You don't really need to characterize your selection function. But to do catalog astronomy, you do. So we hope to put out a large catalog paper and many other related results in a series of papers in the next month or two. So I'll go through these papers in mostly chronological order. So here's our first paper with 13 new FRBs. And at the time, these were at lower frequencies than previous FRB observations. There were a few previous observations that were around 800 megahertz, but almost all of them had been detected at 1.4 gigahertz because popular frequency to search, for 1.4 gigahertz is the rest frequency of the hyperfine line in neutral hydrogen, and so a lot of radio astronomy just happens to be done at that frequency. Now, prior to Chime, all searches at frequencies around 200 megahertz and below had been unsuccessful, suggesting a spectral cutoff. It appeared to be that it was easy to observe FRBs at 1.4 gigahertz, but they were just absent at 200 megahertz and below. But with Chime, we see that around half of our FRBs, there appears to be no preference for flux at the bottom of our band relative to the top of the band. About half of our FRBs are brighter at 400 than 800, and half are vice versa. So it's hard for me to see how the Chime data can accommodate a spectral cutoff. Of course, there could still be a very sharp cutoff just below 400 megahertz. But I don't really see how you'd arrange that astrophysically. Like the usual mechanisms for cutting things off, like free absorption, would not accommodate such a sharp cutoff, especially after you convolve with the redshift distribution of the FRBs. There was a paper, I should mention that there was an interesting paper put out by the ASCAP and MWA collaborations just before our papers came out, where there was a co-observation of a really bright FRB at 1.4 gigahertz by ASCAP. With a non-detection by MWA at 185 megahertz, and that's unsurprising on a per object basis. You can see, like this FRB, for example, you might see it at 600 megahertz and miss it at 400 megahertz. So on a per object basis, it's not surprising that an FRB might be bright at 1.4 gigahertz and absent at 185 megahertz. But viewed as a population, this sample suggests that there's nothing dramatic is happening at around 400 megahertz. And so I personally suspect that the searches at these low frequencies have just been unlucky and will eventually succeed. So because of Chime's low observing frequencies, we make the best measurement of what's called scattering. So if the plasma along the line of sight is turbulent or has small-scale anisotropy, then multipath propagation will broaden the pulse by an amount whose characteristic timescale is proportional to frequency to the minus 4. Here's a scattered FRB in Chime. And around half of our 13 FRB sample is significantly scattered, which you wouldn't necessarily expect. To compute scattering, you would integrate a measure of the amount of small-scale structure in the electron density out to the FRB. And the level of scattering that we see in Chime is higher than simple models would predict if you integrate through like the IGM and the host galaxy. And so this suggests that some scattering or small-scale electron anisotropy is local to the FRB. But we'll be able to constrain this much better when we put out our large catalog paper. We found a new repeating FRB, which was really exciting. Here are 5 pulses from our new repeater. One thing we see that was observed before is that I should say, it's probably obvious, but I should say that when I show plots of an FRB as a function of frequency and time, I've removed the big 0th order delay from the frequency to the minus 2 dispersion. And what I'm showing here is the structure that remains in frequency and time after you remove that big 0th order piece. So after you correct for the dispersion or dedisperse, this is supposed to be, what you would observe in an empty universe if there were no electrons along the line of sight, if there were no dispersion. So in the original repeater, this downward marching substructure was observed, where it looks like the pulse is actually 3 pulses of length of order a millisecond at frequencies that are decreasing. And we see something similar in our repeater. This plot is a really high signal-to-noise measurement taken from Arecibo. You can see that we're noisier. Some of the original repeater, it was the only repeater known for a long time. And when you have a sample size of 1, it's easy to overinterpret. So we found that some properties of the original repeater, like this downward marching structure, are generic and hold up in more repeaters. And some aren't. For example, the original repeater is right next to a persistent radio source, which attracted a lot of speculation. But the other FRBs other repeaters that have been found since then don't appear to be. And this structure actually is something that can be explained in models by some sort of gradient in a plasma. Like a popular FRB model is that a flaring magnetar is attracting electrons to a supernova remnant with shock. And in a model like that you might have multiple shocks with decreasing Lorentz factors as the electrons slow down, which puts the pulses at slightly different frequencies and different shocks. We detected the original repeater, which is not too surprising. Now, when we put our paper out, there was one little puzzle, that the dispersion measure, or the total dispersion delay, appeared to be around 1% higher than previously reported values. And so we seem to be sort of stuck with this. It seemed to be a pretty robust aspect of our analysis, but we didn't really know how to interpret it. And so in our paper, we just list a few possible interpretations. Like one interpretation is time dependence of the dispersion delay, just because our observation is measurements. Another possibility is that our frequency is at our observation is at lower observing frequency. So if the dispersion relation is not precisely nu to the -2, but deviates a little bit, then you might get different apparent dispersion delays when you fit for a nu to the -2 delay in different bands. Or there are more technical possibilities too, like different groups, different definitions of the dispersion measure, different fitting procedures, which agree for a delta function pulse, but might differ for a structured pulse like this. Anyway, it appears to be, so I'm reporting secondhand on results that I've just heard other people report at conferences. But it is my understanding that other groups are continuing to see the dispersion measure go up with time. And so it is, I think it is the case that the dispersion measure of the original repeater is actually evolving in time. And that could happen if the FRB source is ionizing some surrounding medium, for example, and new free electrons are being added to the environment. We found 8 new repeaters. So I should say that there's a bit of a judgment call in deciding whether a pulse is an FRB or not. By definition, an FRB is a pulse that we think is outside the galaxy. And we think it's outside the galaxy because the observed dispersion, that's this column, is larger than the maximum dispersion that we expect if we integrate all the way to the edge of the galaxy. That's these two columns, where the two columns correspond to different models. Now, the galactic models are really complicated. They are fits to a large catalogs of observed dispersions in pulsars. And they model the galaxy in a complex way, like as a disk plus a bulge, plus maybe some ad hoc star-forming regions that are needed to fit the data. And so when our paper came out, I personally felt that the first two sources on the list were about 95% likely to be extragalactic, and the others were unambiguous. Because looking at the first guy, for example, the observed dispersion measure is 350 in radio astronomy units, parsecs per cubic centimeter. Whereas the two galactic models are predicting 200 and 325 respectively. So you might imagine maybe both of them are underestimates, and this guy's really in the galaxy. As it turns out, this particular object, which we now call R3, we now know is an extragalactic FRB, and it turns out to be super interesting, and I'm going to talk specifically about it for a few slides. Here are all the pulses from our FRBs, from the repeaters. Now, one open question in the field is whether repeating and non-repeating FRBs are the same type of object or not. An interesting historical analog is gamma ray bursts. Oh my goodness, I'm like over time. I'm going to have to speed up. Where different gamma ray bursts, long duration and short duration gamma ray bursts, were eventually found to be different types of objects. Anyway, you can see that if you just look by eye at our repeaters and our non-repeaters, then some differences will jump out at you. Like you might notice that the repeating FRBs, we've never observed a repeating FRB that fills the whole observing band. They're always like partial band. Whereas for the non-repeating FRBs, about half of them do fill the whole band. For the paper, the only claim we were comfortable making with statistical significance is that, I'm going to skip this slide for time, I'm sorry, is that repeaters have wider pulses. Here are histogram of pulse width for repeating and non-repeating FRBs. They're obviously different, and the statistical significance is around 4 sigma. I want to use the last 10 minutes to mainly talk about the periodicity results, so I'll just flash through some slides kind of quickly. We found 9 more repeaters, and they were qualitatively similar to our previous repeaters, I would say. All the conclusions held up. This object, the object that we call the repeater that we call R3, that previously was kind of borderline whether it was really extragalactic or not, turned out to be a super interesting object. So the Chime angular resolution is not quite good enough to uniquely identify a host galaxy, Our angular resolution is around 10 arc minutes, and if you draw a 10 arc minute box around the sky location, that box would contain multiple host galaxies. However, we can partner with a higher resolution instrument in the case of a repeater, where we can tell them where to look and they can stare and eventually observe it. And so we partnered with the European VLBI network, a very high resolution telescope, to stare at R3, and they observed 4 pulses in June. And EVN milliarcseconds. So they can tell which galaxy the FRB is in and even which part of the galaxy it went off in. So we know that the FRB is in this spiral galaxy, which has roughly the same mass as the Milky Way. And we can even say that the FRB is in this little V-shaped star-forming region. The redshift of the galaxy is quite low, 0.03, which makes this the closest FRB found so far by a factor of 6 or 7. That is super interesting because what will really advance the FRB field is to identify an FRB counterpart outside of the radio. If you want to do that, then your best strategy is first off to stare at a repeater so that you're not just trying to do this blindly. To search at a repeater that's very active. This is the most active repeating FRB in Chime. And to try to look at something that's close. So you maximize your probability for seeing like optical bursts if they're there. So this FRB, I think, is a super interesting object. It's like the most natural candidate for follow-up, and probably lots of people are thinking about following it up. Now here's something else about this FRB that's really amazing. So this was a total surprise that was found by Dongzi Li, a grad student here at University of Toronto, that the R3 shows periodic activity. Now I want to distinguish between periodicity in the activity of an FRB and periodicity of the pulses. Periodicity of the pulses would mean, say, that every pulse arrives an individual pulse can only arrive at a multiple of some characteristic frequency, which would probably be the rotational period of a neutron star, something on the order of a second. And that's never been observed, and that's not what we see. Instead, we see that the FRB is sometimes active and sometimes active. It's the period during the active periods. It appears to be random when the pulses arrive, but the periods of activity are periodic. We observe this source like every other point on the sky. It goes through the Chime beam for 10 minutes per day, so we observe it for 10 minutes per day. These red arrows show, so this is about a year of daily observations, and the red arrows are what we observe. These are the days when we observe pulses from R3. And the gray bands are not an observation. They're just a set of regularly spaced rectangles that are 4 days wide and spaced by 16.35 days. And not every gray band contains pulses, but the pulses are only found within the gray bands. And that's very statistically significant. It's unlikely to happen as a statistical fluke. To quantify that better, I've imagined that the red triangles were just randomly located. And there are 11 red triangles, so the probability that you would find them all in the gray rectangles by coincidence is 4 over 16.35 to the 11th. That's the width of the rectangle over the spacing. And then I've omitted the details of the trial factor here, the look elsewhere effect, the total number of ways of choosing the frequency and phase of the gray rectangles. And so the statistical significance, there's more than one way of doing it, but I like this way since it's very intuitive and doesn't make any model assumptions. Is around 4 sigma. We did a ton of systematic checks. We didn't observe, you might worry that there's some spurious instrumental source of periodicity, right? So we really bent over backwards to look for spurious periodicity in either the exposure, the times when the instrument was operational, the noise level during those times, or astrophysical things like the number of pulsars detected, which are great because they're sensitive to subtle things like variations in the RFI environment. We do things like make control samples by randomly selecting pulses from bright galactic pulsars. And we don't see any evidence for any sort of spurious periodicity in any of these instrumentally derived quantities. So I'm super convinced that we've seen periodicity and that this is a highly statistically significant result. However, in the original version of our paper, there was something really important that we failed to notice, and we are updating it today. And here it is. aliasing. So when you observe a periodic signal with periodic sampling, remember that we only observe the source for 10 minutes per day, regularly spaced. Then you only observe the frequency after it's aliased. So the red points here are what we observe. We observe the activity of the FRB going up and down with an apparent 16.35 day period. So it's natural to think that the true activity of the FRB follows this blue curve formed by connecting the dots. But another possibility, which is equally consistent with our data, is that the true activity of the FRB follows this orange curve, which is just obtained from the blue curve by changing the frequency by 1 inverse day, or any integer would do. If you sample the blue and the orange curves at integer values of t, they will evaluate to exactly the same points as shown in red. So, as of last week, we now conclude that our assessment of statistical significance is unchanged, but the allowed frequencies are anything on this list obtained by adding any integer to 1 over 16, the apparent frequency. Where the upper cutoff here comes from the fact that we don't just observe for a single instant, we observe for 10 minutes. So if you put these, if you were to put these orange peaks too close to each other, we would start to see like multiple peaks in our observation window, and we could tell. We can't tell with Chime alone. We can never distinguish like the blue curve from the orange curve, even after observing for infinitely long. But it wouldn't take much data outside of the Chime observing cadence to distinguish. Like even one night of data on GBT or something, just tracking the source, could fill in these gaps and distinguish. So for now, we have to say that the period could be 16 days, or it could be like under an hour. But this will be, but other people will observe this. Other instruments will observe this source, and I imagine this will be settled soon. So since it's exactly 5 o'clock, and this is a natural stopping point, I won't subject you to my usual propaganda about how you can build the world's most powerful radio telescope for $15 million, and we can scale this up by a factor of 100 or so in the near future. But these are exciting statements that I believe that are not true outside of radio, and so I think something really exciting is happening in radio astronomy, and the next few years will be really fun. So with that, I'll open things up for questions.